Okay, now that you all are familiar with some of the basic concepts, I think we've been kind of hammering them throughout these last 3 weeks. So today what I'm going to do is the equations, mostly what we have derived, what they're called long channel, um, level 1 equations, first order equations. Um, the present technologies, I mean, forget about the 7 nanometer, even the older technologies like 250 nanometer, 180 nanometer, the equations you are not right, we have derived so far, they're not exactly correct. Okay, so, and mostly to do with the channel being shorter and the oxide being thinner. Okay, that's mostly what the effects are. So what I'm going to do today is, but doesn't mean that the equations are wrong. It's just that we have to refine it. Okay, so refine it to make accurate. But for hand calculations, actually, even for 65 nanometer, you can still use that, maybe to 20 to 30% accuracy, or maybe less, depending on, what kind of application and what regions of operations you're doing. So they're still accurate. I mean, I still use them as a design methodology, and then you use the tool to refine it actually. But you can refine it further by using some empirical approximations, and that's what I'm going to talk about today. And some additional effects like temperature effects, subthreshold current, one or two things. I'm going to kind of give you an overview of that too. So today, I go a little faster pace because these are, a little bit second order effects and additional effects. It's something which, when you're being interviewed, a lot of interviewers, they'll have their pet topics. Like somebody might really love the velocity saturation because that's probably what he worked on for most of his life or got stuck with. And they might ask you on velocity saturation or subthreshold current. So it's not as important for you to know the exact physics behind it. In fact, most of what I'll show you, they're empirical solutions. They're or rather empirical fittings, because for most of these effects, there still doesn't exist a physical equations for it. For example, even the velocity saturation and some of the temperature effects, they are empirical fittings in the model. So people just measure it and do empirical fittings into the models. So, just like what we did for our lab in our when we did parameter extraction, we had a level 1 model. We did some experimentation with spice, and we calculated slopes and all that and fitted in that model, right? Excuse me. So most of the model are refined that way because people still don't have a clearer understanding of, how these effects are um, turning out to be. And because they're very complex phenomena, right? Once you get to really small devices, the interactions are so complex and intricate that it's very hard to create a physical model. So they're all empirical. So what I'm going to show, most of them are actually empirical models anyways. Okay. Okay, so before I go into the the short channel and thin oxide effect, just a quick overview of what we did, and so that we'll be able to appreciate, where the effects are coming from for our equations we have derived so far, right? So for the mass, what we did was we kind of did sort of two separate derivations. In one, we did the VT derivation, the threshold voltage derivation, which was basically the voltage we said above which, when applied to the gate, you're going to get an inversion layer. So if I just had a metal oxide, uh, sorry, I've drawn this um, at the wrong interface. So the the inversion layer is at the oxide and silicon layer. Okay, not this. So what we derived was the voltage of the gate with respect to the substrate at which there will be a channel formed, because this is a P minus. We want to invert the channel to N minus, and that voltage we call it the threshold voltage, which turned out to be this work function difference between the metal and semiconductor, which, you know, in case of IC design, it's poly, and the substrate. And one second, somebody raised the hand. Yeah, somebody has a question. I saw a raised hand, but
No, sir, by mistake.
okay, no problem. So so we derived this voltage, which turns out to be a function of the gate to substrate work function difference, which is essentially like you can imagine as the built-in voltage of the PN semiconductor, then the depletion charge divided by the oxide COX, then the Fermi potential of the 2 times the Fermi potential of the semiconductor substrate. And then, you know, if you remember, when we use this equation, we found out that we actually got a depletion mode device, which in other words, the channel is formed even when the gate voltage is equal to 0. And we want to make a device where, for N-type device, where we want to turn the channel on when the gate voltage is greater than the threshold voltage. So we actually artificially implanted some ions here to make that gate voltage greater than 0. And then there's some impurities, which is small factor. So this is a small factor. This is usually a small factor. These are your big factors, and plus the implant you are doing. And oh, by the way, when I derived, you know, I think my signs were all positive. That's because I was taking magnitude. So I was basically assuming that you're applying VT positive voltages. But just, you know, hopefully it hasn't confused you. Just I would say stick to signs. I think that that way it avoids confusion. So this is the right sign, I think. Um, so this is what we called the VT0, which is when the substrate to source voltage. I haven't shown the source yet. Um, uh, so when both sides of the channel are at the same potential as the substrate, then this is the voltage. Then we added a correction term, which is the gamma times this term over here, which is basically if the any side of the channel is at a different potential compared to the substrate, then your depletion layer actually changes here. And we calculated that depletion layer. What is that extra voltage needed to accommodate that depletion layer? And it turned out to be this function here, which is essentially dependent on this uh, the acceptor concentration of this substrate over here. So this is the VT. So this is what we calculated as the metal oxide semiconductor sandwich. We're not talking about any source drains yet. Then once the channel is formed, oh, I've done the mistake again here. So um, so the source and drains are actually formed here. Okay. So this connection is actually here. So this is, so we use two N plus regions. And so now the channel is formed. We actually want to make a switch out of it. So we said we're going to apply two N plus regions because we have created a N inversion layer. So if you will have an N plus, then if the inversion layer is not there, then it'll be off, in the sense that I cannot conduct between this source and drain. But once a channel is formed, because the majority carrier here is electron, this is electron, majority carrier here is electron, then I'll be able to conduct current through by applying a voltage across this, right? And then, you know, sorry. So this channel is obviously from here. This is the channel, not this. And the channel is basically COX times the excess voltage, VGS minus VT, and whatever, because we're looking at the channel at a location Y. So this is Y at some location Y. So whatever is the voltage at VY, VGS minus VT minus that times the COX is the your channel density here, your um, your electron density over here, right? And this is what we called as a gradual channel approximation, because we assume that the VT is not changing as we are going along, but that's not true. But that's your first order equation. And we did some rearranging and integration of this equation, and we got essentially two regions of operation. One was the linear region of operation, where when VGS is greater than VT, that is, the channel is obviously formed, and VDS is less than VGS minus VT. This is for NMOS. Then this is your current equation, which is a function of VGS and VDS. And we derived, actually, before we derived this, we derived an equation where we said if VDS is very, very small, then this reduces to a linear form, which is mu n Cox over 2 W over L. You can cut this, and VGS minus VT times VDS, right? So this looks like a linear, like a voltage control linear resistor. And as I had mentioned previously, we use this in analog circuit a lot. And then we proved through the pinch-off region, or we showed through the channel, that once this channel area reaches VGS minus VDS is equal to VGS minus VT, then essentially the channel density here becomes zero. So what we call it the pinch-off region, and then the electrons just accelerate through. Then the current is almost equal, and that is the saturation region here, where the voltage condition is obviously VGS should be greater than VGS VT, and when the VDS is greater than equal to VGS minus VT, then you get this almost constant current, but you have a slight, or it's slight or more depending on the channel length and your technology. You have this lambda term, which is empirical term, which adjusts, but the constant. So without that term, it'll be just constant in the saturation region. But we said that in reality, actually, the current kind of increases ever so slightly. I've kind of exaggerated here, and this slope is what lambda is. Okay. So this is what we have derived so far, and we've been using so far. And when we did SPICE simulation, we showed you that when we are, for example, we were um, doing the extraction parameter, and we did 2 times root ID versus VGS curve. We saw that it was kind of like that. It wasn't really linear, and it wasn't really intercepting. So it was true for this small region. And then once the field got higher, then you saw that it deviated away from our equation. And then when it got lower at low field, this is called the weak inversion region, which we haven't talked about, and I'll talk about a little bit very briefly. Weak inversion, and this is called the subthreshold region of operation. So the current is really not zero when VGS is, so this is VT0. Um, so this is an additional effect. And then once the voltage gets higher, the electric field gets higher, then you start deviating as well. And that's what we're going to talk about. And for shorter and shorter channels, and shorter nodes, technology nodes, like when you get to 65 nanometer, 45 nanometer, 28 nanometer, this diversion becomes more and more prominent, and you don't even have this region anymore. So your equations are much more off than what you would get in like 250, 350 nanometer technologies. Okay, I had something here. Yeah. So the key assumptions in deriving this technology was that this horizontal field here, the electric field, which we use to calculate the VT, and then the vertical field here, this vertical field here from gate to the channel, which is essentially VGS over TOX. That's your, vertical field, let's say EV. And then this horizontal field here, which is the drain to source voltage divided by the channel length, or VDS divided by L. And that's your horizontal field here. We basically said there is no interaction between these two guys, okay? But we'll see that once the channel gets shorter and this oxide gets thinner, because essentially we are making the channel length shorter because we want to cram more devices in the same amount of area, right? Right now, like you see, your phone has this Snapdragons, which has 4 billion devices in it, right? In 80s, there were 2 devices in that same amount of area. Now you have 4 billion, I mean, B for B, billion devices inside it. So, and that's due to because of this channel length shrinking and W also shrinking. At the same time, you want to make them faster. In order to make them faster, you want to shrink, you want to make this TOX thinner as well. Okay. And that's where all the process challenges have gone into. And and once you do that, all this assumption of the horizontal field and the vertical field not interacting doesn't hold anymore. And that's where all these second order and third order effects really pop up and make your life harder. And okay, so here I've shown you, this is actually, let me see, I think this table was probably, this I got it from the Hodges book. So I think this was actually in 2004 is when it was printed, around 2005. So up till 2004 is what the technology is in reality. And at 2016 is actually was the prediction. So I thought it'll be a good one to see why, what people predict and what happens in reality, they are not always true. And that has been true actually for everything beyond this too. So in 1995, people weren't predicting this kind of shrinking and the voltage scaling as well. So, so it's the process guys who have, so for example, 1990, you see that the um, the node was 1 micron, right? 1 micrometer. And the VDD, the highest voltage was 5 volts. And your VTH was in the zero point 0.9 volt range. The oxide thickness was about 200 or 250 angstrom, right? And then, you get to 97, 98, then you're in that 180 nanometer range. So at 180 nanometer, your voltage dropped to 1.8 volts. VTH is around 0.5 volts, and TOX is about 35. And by 2004, you were in the 90 nanometer range where your voltage is 1 volt, your VTH was around 0.35, TOX is 20 angstrom. Um, and then the prediction was that, by 2016, you would be around 22 nanometer, your VDD would be down to 0.4, and VTH would be around 0.2, and the oxide thickness would be around 9 angstrom, like 0.9 nanometer, just a few heights of silicon dioxide molecules, basically. That's how thin it is. Obviously, now it's down to like 2 to 4 nanometers. So what I did was, if you just calculate the vertical field, um, which is, I've written here, VDD over TOX, and the horizontal field, which is if you take the maximum VDS, which will be VDD over the L. And if you calculate this is about 250 volt per micrometer. Yeah, 250 volt per micrometer. And the horizontal is about 5 volt per micrometer, right? This is where you started. And as you go along, you can see, if you see the vertical one, it's kind of stayed like almost doubled. And you see it's kind of stayed almost constant around 500 volt per micrometer. Okay. And but if you look at the horizontal one, it's kind of gone from 5 to 10, and by the time it reached 2016, it's almost 4 times of what you had, um, in 1 micron technology. But this is what was predicted, right, from 2004. But in reality, this has not been true. So this is more closer to reality right now, where the VDD is actually almost remain constant at almost 1 volt. So even for the 65, 45, 22 volt, it's almost remain constant. So what it means is that if you look at the vertical field, I mean, it has gone from 250 to 1,000, 4 times higher vertical field. And the vertical field, the horizontal field is even worse. It's like almost 8 times worse, right? So the fields are much higher, and the dimensions are really thin. So your whole idea that this field is not interacting with this and all that is not true. So this looks like a little ball with all the interaction, field interaction happening, right? So the fields are higher and they're interacting with each other right now. And this is primarily to do with the fact that this threshold voltage is not 0.2 volts as predicted. And the reason to do, I mean, the main reason is the difficulty in creating these devices with low leakage current, right? The whole idea of going from BJT to CMOS is that when you switch off a transistor, there's no gate current, there is no drain to source current, right? That's the whole idea of going from BJTs to CMOS. But when you go to finer technology and you drive your threshold voltage to, like, let's say you drove your threshold voltage to 0.2, then first of all, you have gate current now, because once you get to this kind of thin oxide, because of quantum tunneling, you actually have gate current. So that's true now. So we have been assuming the gate current is zero. That's not true with these kind of technologies. Actually, you have finite gate current. Plus, if you went for this low a threshold voltage, you'll never be able to switch it off, primarily to do with process. You just won't be able to, dope those areas to such precise level in nanometer dimensions, such that when you take your VGS to zero, IDS is going to be zero. And that's what has, kind of kept this voltages constant, because they wanted higher VT voltage. If you want higher VT voltage, then obviously you want excess gate voltage to drive higher currents, because people are wanting faster devices, smaller devices, faster devices, and they're all basically resulting in this sort of conflicting um, parameters. And so the balance has been, the volt is staying at around 0.91 volt, the threshold voltage around 0.3 0.4 volts, and which has resulted in these higher basically fields. Okay. So the two major effects which is has resulted from these higher fields and shorter basically um, uh, lengths, which is basically making it to interact between those two regions, is that the mobility is degraded now. So and the mobility is directly related to the current, right? So the voltage you give, um, so your IDS is mu times Cox Vgs minus Vt whole square. So if your mu is lower, for the same given gate voltage, your current will be lower, which means that in a digital sense, your resistance of that MOS switch is going to be lower. So your time constant will be higher, which means that you cannot switch it faster than what you want, right? So that's the result of having a mobility degradation. And the second thing is, because of these high horizontal fields, you also get on top of it velocity saturation, where what it means is that in our long channel approximation, we said we reach the saturation, that is the current is constant when the pinch off region happens. But because of these high field regions, your velocity actually saturates earlier than that VGS minus VT. And we'll do a small example to kind of show you the effect of that. So these are the two main sort of effect which hampers your the device operation. So essentially your device operation degrades because of these two effects. So what we're going to do is we're going to take a look at what are these two effects and give you an idea. So I'm going to follow the Hodges book pretty closely on the next few slides, so you can you can go back to the book and refer to it if if you have any doubts. But stop me if you have any questions, obviously. Okay. So what has resulted is, like as I said, the currents have been decreasing um, for the same given uh, VGS voltage. So if you look at the drain current versus VGS, you remember it is a square law, right? So it kind of does this square law. But once you reach this high field effects, it's actually more linear than square law. And you saw that when we did the root ID plot, you can see at the higher plot, the root ID plot kind of flattened out, which means the square of that is more linear in nature, right? And same thing with the VDS versus ID equation. This this flattening of the curve happens earlier than what you would have predicted with your long channel prediction. So your long channel prediction might have predicted that the constant current happens over here, but actually in reality it happens earlier because of velocity saturation, because of which, so now you have the current dropping and the becoming constant at earlier voltage. So both of them result in essentially lower current drive, or in kind of a digital sense, your switch resistances are actually increasing, and so your speeds are actually decreasing, or your delays are increasing, so your speeds are actually increasing. Okay, so I'll just quickly show you again. This is what is shown, is derived in your Hodges book, the reference book we have been using, or the textbook we have been using. This is kind of a empirical formula for people to use for hand calculation. But if you look at the model, it's a lot more complicated. And I'll show you the BSIM4 model at the end of this lecture. I'll open up the manual and I show you, how complex each of the equations are. And that's why, instead of 5 parameters, you have 100 parameters, like in BSIM3, and in BSIM4 it's even more. Okay, so essentially, for the higher field, we're going to calculate and we're going to call it mu e, which is mu effective, which is going to be mu naught, which is your nominal mu at low field. So which we have been assuming so far. And then we're going to add this correction term. And this correction term is actually going to be dependent on this term here. And the VGS minus VT over TOX is nothing but your vertical field. So it's your excess vertical field, because this is your excess voltage divided by TOX. So your excess vertical field. And and we add this empirical term here called theta, and this theta obviously will be the unit has to be volt per meter, which is electric field, because you want to make this term unitless, right? Because this is mu naught, so if mu needs to be the same unit as mobility, then I want to make this unit unitless. So this theta is going to be volt per meter. This is going to be empirical term here, and some theta times and some eta, which is basically, again, these are empirical terms depending on your technology and how you're doping and all that. You basically derive these terms from your process parameters. So essentially these two are empirical terms. So this is a unitless term. Like I said, this is volt over meter, which will be given for each technology. And like I said, this whole factor is to reduce your mu naught for high vertical fields. Basically, that's what you're trying to model. So here I've shown examples. So let's say your low field mu naught was 540 centimeters square per volt seconds. And let's say the theta, this is an example from your book. I think for 0.18, this is what theta is derived. So it's 3.6 basically volt per centimeter, 10 to the power 6 volt per centimeter. And eta is 1.85, TOX is 22 angstrom, which is I think 0.18, and VGS minus VT, let's say, is 0.8 volts. That's your excess voltage. So if you plug these values and do the calculations, you'll see that your effective mobility drops to 270, which is almost half of what this is, right? So that's how bad it is. And if you look at the BSIM3 mobility model, this is kind of a mobility model. And like I said, these are all fitting parameters. There is like I said, the physics are so complicated. They don't have physical equations here. They have fitting parameters. Okay, so they have all these fitting parameters: mu UA, mu C, mu naught, mu B. And after the chip comes back, the test structure, they measure and they bin it and do a lot of, just like we did with our extract parameters. So it's a lot more complicated version of that, where they do all that fitting and they get parameters for mu A, mu C, mu B, and so on. Okay, so so that's the vertical field part of it. So I told you there are two effects. One is your mobility degradation, which I just showed you. The other is the velocity saturation. Now, when we wrote the equations for your relation between uh, the velocity with the electric field, the constant of proportionality was this mu, right? So so if your velocity is basically this slope, if you take velocity versus the electric field, that's what I've written here, then this slope is this proportionality constant, which your mobility of in case of an channel, it's the mobility of your electrons, right? Now, we assume that this velocity will keep going up and up and up and up if your electric field goes up and up and up. But at very high electric field, this starts saturating and velocity just saturates, and mostly to do with the lattice vibrations of your this thing, because the more the electrons carry speed, there's more lattice vibrations and you have more what's called phonon energy, and so it's like a terminal velocity on second order terminal velocity. So mu is already a terminal velocity, this is on top of it. So after some time your velocity just saturates, doesn't matter what your electric field is, and that electric field, we call it the critical electric field. Okay, critical electric field. So EC is that term. So here is an example of like electrons and holes in a particular technology. You can see that the saturation velocity is around 8 to 10 to the power 6 centimeters per second for holes and electrons. And you can see the electrons actually saturate a little faster than the holes do. And because of which, so even the mobility is lower for holes compared to electrons. You'll see in shorter channels. So, it's a 4:1 ratio or a 3:1 ratio. But since the velocity saturates faster, you'll see that the ratio for smaller nodes like 65 nanometer, 99 nanometer, and so on, the ratio is not 4 anymore. It's close to 2 now because of this velocity saturation. Okay. So we have so the ECN, the critical field for the N type is typically around 6 into the power 10 to the power 4 volt per centimeter. This is one example. Obviously, it depends on the process and so on. And for hole, for example, it could be as high as 24 into 10 to the power um, 4 volt per centimeter. Okay. And to kind of give you a first order modeling of this so that you can use somewhat in your hand calculation. So this is modeled as a piecewise linear. So you have this piecewise linear where you basically use the mobility equation like you do for low fields here. So this is a piecewise linear equation where for low fields, it kind of asymptotically equates to here. For high fields, it becomes constant, it becomes VSAT. So it kind of asymptotically joins to VSAT. So this equation kind of does a piecewise linear for that. So you can see that, if this EY is much less than EC, then mu is V is equal to mu times EY, which is our earlier equation. And then if EY is much, much greater than the EY cancels, then this VSAT, we can equate it to 2 times VSAT is equal to EC times mu E, which is basically this equation for the condition that the horizontal field is much greater than this critical field here. The critical field is this field where it is saturating. Okay. So, and these are, like I said, these are all empirical. So you kind of get these terms, the EC values and this critical field values, you get it from VSAT values, you get it from after the chip is fabricated, you measure them and you get it. Okay. So we kind of did two modifications, one to our mu E, and then then we introduced another term called VSAT, which is basically saying that a velocity is not going to keep increasing, but it'll saturate at some time. So if we put this in our current equations, which we have been deriving, if you remember, for our long channel approximation, we said first we apply a voltage at the gate such that we get some charge And this charge is VGS minus VT times Cox times V over Y, V of Y. So this is V of Y because the voltage is going from the source. So basically you're going from VD to 0. So the drain voltage to source voltage in the channel is kind of linearly decreasing from the drain to source voltage over here. So we call that V of Y. And then we did some rearrangement and integration to get those equations, right? Sorry. And we kind of took this channel, the 3D version of this channel, and we took a slice here, and we calculated the channel density, I mean the charge density here, and then we said, the electric field is a certain electric field over here, and that times mu is the velocity of the electrons. So we calculated the average amount of electrons passing through this cross section area, and that was the current we derived. So we do the same thing here, but instead of um, the V, we put this value V sat here, which is this corrected term which we use in the last slide. So it's mu E times the horizontal electric field times divided by 1 plus the ratio of the horizontal field by this critical field, which is derived empirically from here. And this mu E is that term where we derive that mu naught times 1 plus VGS minus VT over theta times Tox times some eta, right? So these two we kind of integrate into the thing, and then we do the same sort of rearranging and integrating. And when we do that, we get this equation, and this is our linear equation now. So this is our modified linear equation. So VGS is greater than VT, but VGS is less than VGS minus VT. And you can see that this is pretty much the same equation. If for low fields, this turns out to be the same equation as we did before, because at low fields we said mu is equal to mu naught, and VDS is basically much less than the critical field times the length of the channel, because this is by definition, because this is how we defined it. So this turns out to be W over L mu naught Cox times VGS minus VT VDS over 2 times VDS, right? This was our original equation. So all you had to do is add these two correction terms. So we add a correction term to the mobility, and then we added a correction term to the velocity saturation by adding this, and that kind of gave you a approximate equation for your short channel and thin oxide term. Okay. For your saturated equation, instead of using the VGS minus VT, we actually use the VSAT term now. And the VSAT term is what we derived in the previous equation. So and because the current is going to be constant because it's saturated right now, and so we substitute Vy equals to VDS, and so equating IDS in the linear region at the V saturation region, just like what we did for our long channel approximation. So we said, okay, we know it is constant, and we know where it becomes constant, right? For example, in the long channel, we said it becomes constant here. So we apply that VGS equals to VGS minus VT in the saturation current equation and got the equation, right? Here we do the same thing, but instead of VGS equals to VGS minus VT, we basically substitute the VSAT term in the linear equation, and your VDSAT is now, sorry, VDSAT now is this term over here. And if I rearrange this term, you can see it's VGS minus VT 1 plus VGS minus VT over EC over EL. And this obviously turns to VDSAT is equal to VDSAT, let's say, uh, I'll call it VDSAT naught, which is the low field VDSAT, right? And this is for when VGS minus VT is much, much less than ECL, which is our definition for low field. So essentially what we did was we have added a correction term to the mu and Cox term, and for the linear equation and for the saturation equation, we added correction term to the VDSAT equation. And that's what is. So but now, for short field, this is how you're going to calculate the VDSAT instead of calculating with VGS minus VT. right? So you're going to use this equation to calculate the VGS minus VT, which is going to be at a lower voltage, obviously. Okay. So substituting this, so this is your entire saturation current equation, which is basically is the same thing. VGS should be greater than VD, and VDS should be greater than VD sat. But this VD sat is now this term here, not VGS minus VT, the correct term. And for low fields, again, you can do the same approximation. If you make sure that the VGS is VGS minus VT is, VGS minus VT is much less than ECL, then this reduces to our earlier equation, and you can substitute mu naught over here, and then you get our old long channel friendly equation, mu naught over 2 Cox times VGS minus VT whole square. Okay. All right. Any questions? So, like as I said, if you're getting lost in the equation, don't worry. But basically, remember what we are trying to do here. We are trying to find some approximation to the high field and the short length and thin oxide effect, so that we can make changes to our earlier equation to give us a little bit more closer to real numbers than what we have been calculating. Okay. So, any questions so far on this, what we have done? So what we did was we made a correction to mu, and we made a correction to the velocities of the saturation. So it's basically a double correction. So your mu got degraded, so your velocity already decreased because velocity is equal to mu times the electric field. Then on top of that, we said now even with this degraded mu, it's still not going to go on and on forever. It actually is going to saturate at a lower field than what we had calculated before because of these high fields. Okay. Any questions? Any part absolutely didn't make sense, or everyone okay with this? All right, let's take an example. So actually, why don't I give you some numbers? Let me see. Okay, so let's take the data for 0.18 is in the book. So let's take a 0.18 micron example, the CMOS example. So let's take a NMOS, and we're going to apply some VGS and VDS. So let's say 1.8. So let's take let's take 1 volt and VDS to be 1.8 volts. So we'll just take the high field 1 volt, and W over L will keep it 1 micron by 0.25. So it's a nice W by L 4 number here. So what we want to do is now we want to, so obviously this will be in saturation. That's the way I biased it. So we want to calculate the old way, ID sat long channel, and use our new set of equations, the short channel equations, and we're going to calculate those, and we'll figure out what is the difference. Okay. So let me give you some parameters. It's the table, you can grab it from, I put it on the GitHub page, but let me just grab it from the book and give you the numbers. So 0.18 NMOS, so VT, yes. So VTN is equal to 0.5 volts. your mu naught, the low field mu naught is 540 centimeters square per volt second. And mu E. So this is already calculated for you. So this is the same calculation I did 3. So you don't have to do this one. And the critical field EC is equal to 6 into 10 to the power 4 volt per centimeter. And ECL, because we is equal to 1.2 volts. So it's already calculated for you. Okay, and C aux is equal to 1 microfarad per centimeter square. Okay, so do this calculation. I'll give you some time. So like as I said, use, let me write, well, actually start doing the first equations. So let's see what current you get. And then I'll maybe give you the other equation. And you can obviously neglect lambda. Here we're assuming lambda is a small number. Okay, how many of you have the long channel current? What is the current? Anyone? How many of you are not sure about the long channel saturation current equation? Okay, Ashwini, 0.912, so 912 microamps. Okay, we got one answer. Who else? How many of you don't know the long channel saturation current equation yet? Raise your hand. Okay, looks like everyone knows it. Okay, so why are you not able to calculate? So how many of you still don't have an answer? Raise your hand. I have a feeling you guys are not there because you're saying you don't have a doubt, you don't have an answer. I don't know what you're doing there. Okay, for long channel, first tell me, what is the condition for saturation? How do you know it is in saturation? Anyone? This group has gone like completely silent.
Please
Okay,
respond at least.
okay, maybe let me pick someone. Okay, Alok, what's the condition for saturation? What condition has to be made for saturation? Okay, Ashwini, why don't you go ahead before you're saying something, Ashwini?
Sir, not sure about the long channel equation.
Oh, you're sure about the short channel, but not. How did you find the number? How did you get to 912?
Sir, I use the formula mu1 x by 2 W by L VGS minus 50 whole square.
Okay, but what is the condition to use that? There are two formulas, right? What is the condition to use that formula?
This is the gradual channel approximation formula, I think.
Yeah, but what I'm saying is that what is the voltage? So I've given you a VGS equals to 1 volt, VDS equal to 1.8 volts, VT as 0.5 volts. How do you first assume? I said, I have made sure that it is in saturation. Now I'm asking you, have I made that assumption correctly, or I have a problem with that? Okay, I'm going to go one by one. You guys have to answer now. Srishti, Srishti Rani? What's the condition for saturation? What condition has to be made for saturation?
Sir, VDS should be less than VGS minus VT.
For saturation and for
Yes,
linear?
sir. VDS should be greater than VGS minus VT.
Okay. So why didn't you come and just say that? Okay. How about Pragya Rath? What do you think is the condition for saturation? Okay. Thanks, Srishti. At least You gave some answer.
Thank you, sir.
How about Pritham? What's the condition for saturation? I think these guys are just switch it on and disappeared. Rinky, what's the condition for saturation? Oh, Pritham, yeah, go ahead. Sorry. Pritham, you wanted to say something? Okay, Rinky, go ahead. What's the condition for saturation? Go ahead, Rinky. What's... Yeah, we can't hear you. How about Shruti?
Sir, VDS is more than VGS minus VT and VGS is more than VT.
Okay, good. Why don't you just come on and answer? How about Alok? Because we have heard two answers now. Alok.
Sir, VTS should be greater than VGS minus VT.
VDS should be greater than VGS minus VT, right? And VGS
Sir,
should be
greater than VT.
greater than VT. Okay, good. So why are you guys not saying? So that's the condition. So the condition for saturation, the long channel, which we have been doing so far, is first thing is that obviously you want to make sure. Let me just use another color here. First, you want to. So this is we are doing long channel, which we have been doing for last 3 or 2 weeks now. Is that for condition of saturation? Is first obviously both for saturation and linear region, your VGS should be greater than VT, right? Without the channel formed, doesn't matter what VDS is. So VGS should be greater than VT, and then VDS should be greater than VGS minus VT. I forget who was the first one who came and said VGS should be less, so it should be greater than, because that is when it is pinching off, right? The higher the field goes, so you have a nice channel, uniform channel formed from source to drain, but as you're increasing your VDS on your drain side, right? So if I draw the channel here, you have a nice channel formed like this, and then as you're increasing your drain side, this side slowly starts tapering off because this side channel voltage is less than VGS minus less than VT. Okay, get to channel voltage, and at one point it is going to pinch off, and that's this point here, and after that the current is going to be constant, right? And what is the equation for the current for the long channel? It is IDS equals to mu naught Cox over 2 W over L VGS minus VT whole square, right? 1 plus lambda term, we're neglecting it for this equation. Okay, so let's plug in the values now. So mu naught is 540 centimeters square per volt second times Cox is 1 microfarad per centimeter square times W over L is, so this is going to be unitless, so that's 4, and then VGS minus VT is 0.5 whole square, right? So this will be centimeter square cancels, microfarad per second becomes microamp. So this will be 540 times 4 times 0.5 whole square, which is half square. So this will be half by 4. So it's 540 microamps. Sorry, I'm missing.
Excuse me, sir.
1 second. NCX, yeah, I'm missing a two term here. 500 by 20, which is about 270 microamps. Is that correct? Is everyone getting this? Yeah, go ahead, Ashwini. What's the question?
So mu naught is the mobility of holes, and mu is the mobility of electrons. So we'll put mu e here.
No. So usually when you're talking about mu n and mu p, that's when you say it's electrons or holes. Mu naught is, I'm saying that it is electron mobility, but it's the low field electron mobility, which I've already given you 540 centimeter per volt square. So that's what I've given you. Okay.
Okay, sir.
Everyone agrees with this number, or anyone has a different number before we proceed to the, raise your hand who has calculated and got the same answer. Come on, you guys got to calculate this simple equation here, right? Okay, good. Who else has calculated and got the same answer? I want at least, a couple of hands up before I move on. Okay, who else? Okay, all right, I hope you have calculated. All right, so this is our long channel one. For the short channel one, first we have to find out so I'm going to give you the equations and I'll allow you to do the calculations for some time and then tell me what your answers are. Okay, so let's do the short channel now. So we're going to do our short channel calculation here. So for short channel, if you remember the last slide, I'll just rewrite it here again. The VDSAT equation is this now, right? So it's VGS minus VT times EC times L. But I've already given you the EC times L number here to make your life easier, which was from the table, obviously. VGS minus VT plus ECL, right? So this is your condition for saturation. So first calculate this and figure out if it is in saturation and what is VDSAT. If you are happy that yes, it is in saturation, then you're going to use this equation now. IDSAT is equal to W times the saturation velocity times Cox times VGS minus VT whole square divided by VGS minus VT plus ECL. Okay, and VSAT we calculated as so VSAT is equal to EC times the effective mobility by 2. Okay, so first calculate VDSAT, find out what this voltage is. That should be pretty straightforward. Once you're happy with this, then use this equation to calculate the current, and let's see what the current comes out to be. All right, I'll give you guys a couple of minutes to work it. So if you have any questions on the equations, just let me know.
Sir, please allow us to rename.
Sorry, what was it again?
Please allow us to rename, sir.
I thought you're allowed. Okay. Oh, somehow it got. Yeah, you should be able to do it now. I don't know why it got. Okay, so VD-SAT 0.35, 3.5 volts. Yeah, anyone who's getting, so this is where I say you have to do sanity check, right? If your VD-SAT is greater than your supply voltage, then you're definitely wrong, right? Because it should be less than, first of all, you realize, right, that the equation is less than VGS minus VT. So it has got to be less than 0.5. So if you're higher than 0.5, you made a mistake. So just check your equations. So 0.35, 0.35, okay, good. So everyone got VD-SAT equations correct. So obviously VDS is greater than VD-SAT here, and you can see now the VD-SAT happens earlier, right? In case of the long channel, we said the saturation is happening in 0.5 volts, but in reality, it actually is going to happen at 0.35 volts. Okay, so now calculate the current. So now that we know it's the saturation region, so good, everyone at least got the VSAT. Now calculate the saturation current. And to write the saturation current, what you can do is you substitute the VSAT into the equation and do some rearranging to make it simpler so that you can use your previous result quickly. Okay, good. Everyone got 0.35. Now start deriving the equation for ID-SAT. Okay, like I just said, you you have to do some sanity checks. So when you get answers, so Shruti, when you get answer 4.76 amp, you have made some unit mistakes because first of all, we have calculated 270 microamps right before, and we know that because there is a mobility degradation and velocity saturation, it's actually going to be lower than 270. So same thing with you, Srishti, right? You have 1100 microamps, right? 11,000 microamps, but it has to be less than 270 because either you don't agree with the 270 number or you agree with it and you correct it, but you can't be, both can't be right, right? Anyone else? Okay, Ashwin says 119. Okay, at least that's less than 270. Who else? Okay, Subrajita says 190. Okay, it's less than 270. Like I said, when it's less than 270, you know, at least you know that it's not way off. There might be still some errors. Srishti says 238. Okay. All right, so maybe let me calculate and see what I get. So in order to, you know, kind of minimize mistakes, it's always best to kind of get into units which you are acquainted to, or even get results which you have already done, right? So for example, so let me rewrite this ID sat here. So ID sat is equal to, so if I substitute VSAT is equal to EC mu effective times 2, so then it's going to be W times EC times mu E over 2 times Cox, then VGS minus VT whole square divided by this correction term, which is VGS minus VT plus ECL, right? Now, I already see that I got mu C ox W. So what I can do is, so basically if I can use this result, then my chances of minimizing error or getting to the result quicker is more likely, right? So I see that I got mu C ox over 2 VGS minus VT, but I want W over L mu naught C ox over 2 VGS minus VT to get there. So let me see if I can, so let me switch to maybe another color here. So I'm going to do divide by L and multiply by L. So I got W over L. Now I want mu naught. So I'll do mu naught and divided by mu naught, right? So you can see I have W over L mu naught Cox times VGS over VT square, which I'll call it as ID0, let's say. Okay. So then I can write this term as ID0, okay, and then see what I'm left with. So I'm left with EC times L, and then mu E over mu naught ratio, and then divided by VGS minus VT plus ECL, right? And you know, whenever you do this, just make sure all the units make sense, right? So you want this to be in microamps, right? So this is or ampere. So this is in microamp. Now you have a voltage here, unit less here. So this is voltage, but then you have voltage plus voltage. So the units voltage will cancel, and then you'll have microamp. So at least unit wise, this makes sense. So okay, now I substitute the current I had 270 times ECL times mu E over mu naught. You see mu E over mu naught is roughly 0.5, right? So 1.2 times 0.5 divided by 1.2 plus 0.5. Actually, magically, I don't know if this is by coincidence or this is actually real. I actually don't know myself. But this number we actually have calculated to be 0.35. So 270 times 0.35 is, what is it? 270 times 0.35 is 94. Yeah, go ahead. Somebody had a question. Roughly 94 microamps. Does everybody agree with this? So you see what I did? I just rearranged the term to actually get it to what I had calculated before, and then the correction term, right? In the correction term, you can see 0.35. That's only 35% of what I had calculated. So it's 70% off, you know. So it's quite off, but at the same time, as a designer, you're, you can still be in the right direction. Like as I said, you could be still in the, especially if you're using long channels. If you're using channel lengths of 1 micron plus, the ECL value which you have taken is actually for the shortest channel. The ECL value will actually change for longer channels. So so you can see that the difference is, almost basically 70% off, right? Because 0.35 is only 35% of what we calculated previously. Okay, everyone clear with this, or any questions? Did you get how how I got this? Basically what I did was I just added some terms to make it this number plus some constant times that, rather than calculating everything again, right? So looks like few of you got 95, 95. Okay, good. So at least it seems in the same ballpark. Okay, makes sense, everyone. So you can see that by, especially with short channels, and this is 0.18, as you go shorter and shorter channels, like as I said, you're going to be way off compared to this. Now that doesn't mean that the long channel equations are completely waste. They still allow you to predict a lot of your design methods, and which direction you're going in and so on. It just so that it won't give you the accurate result. You still have to use a simulator, but you can use at least these short channel equations to large extent to get it closer to. So when you are doing now tau calculations for your inverters, let's say for 130 nanometer, you can use these equations now to get to a closer value. Okay, everyone follow so far? Any questions? So yeah, those of you got higher numbers. So like I said, your sanity check would be, you have already proven yourself that the equation should give you lower number, right? Because your mobility is degraded, your velocity saturation is a lower number than VDSAT of before. So you should get a lower number than 270. If you're getting lower number, higher number than 270, that either you have made a mistake in your current calculation or you have made a mistake in your long channel. So you have to, check either one of them, but you can't say this is correct and that is correct, right? It can be. Okay, everyone follows so far, or any questions? So like I said, even though some of you are not following the exact terms and all that, just make sure you understand the principle behind what's behind the, so it's the mobility degradation and velocity saturation. So like, for example, in an interview, if somebody interviews you and says, okay, these are long channel approximations, what are the two main things which is going to change? If you just know that, then they're not going to ask you like, okay, what's the mobility degradation equation? Even they ask you, you fail, they're not going to hold you up against it. But if you say, yes, the mobility is going to degrade and it's going to be a smaller number, and it could be as small as half, and your velocity saturation, your electrons are going to saturate earlier than your predicted VDSAT before, most people will be very happy with that answer. They'll know that, okay, at least what's going on with the short channel. Okay, and most interviewer probably they'll themselves may not have done these calculations. Okay, so here I'm just showing you one effect of like as I said, because so I think I showed you this slide before here. Yeah, this slide here. So what I showed you is that you basically the electrons actually saturate at a earlier velocity, like 6 times 10 to the power 4 volts centimeter compared to the holes. Although the holes are slower, so you can see the slope is smaller than the electrons here. So typically that's, this is in a log scale, but in a long channel sense, it could be as high as 4 times. So the mobility of the electrons are 4 times higher than the holes. So in other words, for the same VGS, you're going to get 4 times more current, right? But the thing is that because you have it in the saturating faster, in saturation, it's not going to be 4 times now, and that's what you're going to it's shown in this curve here. If I go back here, basically what it is shown here is that you had some current with 1x MOS, and you take a 1 MOS PMOS, and you have some differential in the current, and you keep increasing the size of the PMOS. You can see by the time you get to 3x, your current is almost equal, although the mobility difference is 4 times. And here there is exact calculation which shows you that it's around 2.4. So in other words, when you're doing device sizing to, inverter sizing to get the exact TPLH and TPHL. So you want your, for example, in an inverter, right? Inverter, 1 second. So there's a question from Ashwini. Can we convert each terminal into SI units for calculation? I mean, how to simplify the calculations? Well, I showed you, right? Instead of going through the units, yeah, just make sure the units are canceling, right? So if you have one in centimeter square per volt second, then have the other one as farad per centimeter square, instead of having farad per meter square and doing meter square in each one of them. And so always have units which can cancel easily, and that's the way to do it. And that's what I showed you. So in case of an inverter, for example, so when Santanu was showing you the delays, you see that you had effective resistance here, like RFP, let's say, and this was some effective resistance RN, right? So you have the same cap. So you had a charging time, which we call it tau P high to low. Low to high, and then you had a discharging time, which we call tau P H to L, right? And typically you want these to be same, right? You don't want them to be hugely different. Now, because the mobility, let's say the mu n was equal to 4 times the mobility of the P, then you want this WP to be 4 times WN, right? In order to compensate that mobility, keeping everything else constant, right? Because the VGS, when you take the input from 0 to VDD and VDD to 0, VGS is the same, COX is the same, VT, and let's assume that VTN is equal to VTP. If you assume all that, then you want to size the W to be this. But then for short channel with this velocity saturation phenomena, you can see that you really don't have to make it 4 times, because this costs you in area, right? You really have to only do it 2 times to equate the thing. Now the overall delay is larger, but you can't help that. But now to equate it, instead of doing it 4 times, if you just approximately do it 2 times, you'll be very close to equating both the delays. Okay, so that's what this curve is showing. Any question on this one? Okay, so that was the effect on the current. Now there is an effect on the VT as well for a short channel, but it's actually to do with your doping profile rather than anything to do with your fields. The field part is captured in the currents actually. So what happens is the VT equation we derived, right? So if I write that VT equation here, let's say you have phi GC plus minus 2 minus QB COX minus 2 phi minus Q DI over COX and so on, right? So two main ones are these ones. So obviously the work function difference is, it is what it is. The high field doesn't make any difference. This one, this factor over here, the QB COX, which depends on the, which has a huge difference on the VT when you're applying a substrate bias voltage, actually depends on how linearly is this channel graded here, right? This, so you can see this is a sort of a 3D picture. This is actually in your Kang's book. Actually, I'll send you a PDF soon. This is showing you the gradation. So the calculation we do for gamma, it assumes that this channel is graded evenly all throughout, right? So the N channel N sub is graded, or the N sub happens at a much higher distance. But once we make the channel shorter, this gradation is not uniform as much. So you actually see the gradation at a lot lesser depth than you used to in a longer channel. So in your longer channel, this depletion will almost look like this. But now you have this gradation because the channel lengths are squeezing so closely that when you do these channel implants, they don't dive that much deep into the substrate. So because of that, again, this is again empirically done it. So you get two gamma factors, one gamma for near the channel range, one gamma near the end sub. And then this is in BSIM3. I'll show you when in BSIM4 it's even more complicated. Two constants are calculated, K1 and K2, which is function of basically phi, which is 2 KT times 2 KT over Q, times the natural log of the intrinsic carrier over the n sub or nch, n sub here in this case. And then gamma 2 and gamma 1 is these two factors over here. So you calculate, and these are complex functions of that. And then the VT, which was before VT0 gamma, this was gamma times phi minus VBS minus phi EF. And now it's K1, this constant times this one, minus K2 times VBS. Okay, so you are adding two more terms a constant. So the VT0 still remains the same. Actually, the VT0 also has a factor, but in BSIM3, you'll see that it is almost close to VT0, and then you have these two correction terms. So in other words, the short channel, because of this gradation, you also have effect, which you see only when you apply a bulb to source voltage. Okay. The other effect which you have is when you get really short channel, this is called a classical short channel effect. And this is because of the depletion slowly moving closer and closer, which is not captured in the previous equation actually. Your VT actually starts dropping. Okay. But there is actually an effect which makes it go higher too. It is mostly to do with oxidation enhanced because of the diffusion around the channel. Okay, these are, and this is known as the reverse short channel effect. So that's why you'll see when I'll show you the BSIM4, it has a very complex function of WL and all these derived parameters. So it's a very complex function of all this. So I'm just kind of showing you what are the other effects you can actually have. So as your width is decreasing, I'm just showing you the length, but as your width is shrinking, then you also have a lot of doping effects and high field effects, which results in your VT being different than it would be in a long channel effect. Okay, so another effect which has on the threshold, it's called the DIBL. And again, DIBL, I'm just going to explain to you just the nature of it. Will not go deep into what DIBL is, but like I said, most of the time people just ask you in the interview, what's DIBL, and if you just know the nature of it, most people will not ask beyond that. So what I've shown you here is actually the so if I draw the channel here, let's say this was an NMOS. So what I've shown you is actually the conduction band of an NMOS as you're traveling from the source to drain, right? So this is the source side, this is the drain side as you're going along. So this first dotted line you see here is when your VGS is equal to 0 volts or it's flat band basically. Basically, you're not switched on the channel yet. Okay. So, and if you haven't applied any voltage, so if your VDS is equal to 0, then this is how the dotted line is going to look like. Essentially, this is the potential barrier. So that's why you don't have any conduction from the source to drain, because you have this potential barrier. So, and when you start applying a gate voltage and you start applying a gate voltage greater than 0, then this barrier slowly starts coming down. And when your VG becomes close to VT, that's when the barrier completely overcomes, and now the conduction will take place. This is assuming that your VDS is equal to 0. In other words, source and voltage. Now, when you apply a drain voltage on top of it, this barrier even comes down further, right? And that's how you get the conduction, right? Because of this potential slope, your dphi over dt gives you electric field. So E is equal to minus, dphi over dy, and this electric field, so mu times electric field is your velocity of electron, and so on and so forth. We did all this calculation, right? That's why you get the conduction of the electron. But the effect it has on VT is because the VT is really dependent on the potential barrier at this end. And you can see with the long channel, the effect here is not that much. It's just having the effect on the drain side. But now when you go on the short channel, like this is the short channel version again. So you same thing again, you have the drain, you have the source, but now a channel is much shorter. But when you're applying the drain voltage, this drain voltage, now you'll see if I uh, zoom this, you can see that this barrier now is dropped, and the effect of that is VT is now dropped also. So VT is slightly lower than compared to your long channel. So here, I've shown you a graph over here in long channel. As your VDS is increasing, your VT is actually constant. It is not changing, remains the same channel. But for shortened channel, as your VDS starts increasing, your effective VT also changes, and that's captured in your VT equation, in your VT models basically. And that's what's called the drain induced barrier lowering. So basically your drain is inducing a lower barrier to conducting current. So if you're lowering the barrier, that means it's easier to conduct current at a lower VGS voltage, which means your VT, effective VT, is going down. That's really the effect of DIBL. Okay, so drain induced barrier lowering. Okay. All right, any questions on these two effects, what we have discussed so far? The short channel equation, threshold equation, because of the gradation, and this is really a phenomenon I've just told you. I haven't shown you any equation or anything like that. Like I said, they are complex fitting parameters really, but just so that you know the physics behind it. And this is the DIBL, the drain induced barrier lowering effect. Any questions?
Sir, in the first graph,
Yeah.
why that third number line goes down means the value of E decreases suddenly.
So this is for larger and larger VDS. So basically, when you so you can imagine that so when you're applying a voltage, essentially you're lowering the field because your your potential is the potential of a positron or a hole, you can say, which means that the electron potential is lower than that, right? So as you're increasing this voltage, so you're applying a voltage here to the source, your potential of positive potential goes up, but which means that the electron potential goes down by the same amount, Q times VDS. Okay, so when you're looking at the conduction band around here, so the conduction band potential goes down, and conduction band by definition is the potential of your electron, right? So your potential of your electron is the reverse of the positive voltage, so it's going down by the same amount. And if it goes down, that means the potential for you to conduct positive carrier now goes up, right? That's essentially what you're doing. So if you have not given any potential here, then it would be just flat, right? If it is flat, then d phi by dy is equal to 0. There is no electric field, so there will be no current, right? So let me draw it here. So what I'm saying is that, so let's consider VGS equal to 0 and VDS equals to 0. Okay, so then your barrier is looking like this. Let me draw this in. Draw this in red here. So for VGS equals to 0, well, so VGS equals to 0, or maybe flat band, and VDS equals to 0. Your conduction band, going from source to drain is going to look like this. And conduction band is the potential of electrons, right? So basically the potential of electrons here is lower than the potential of the electrons in the channel, which means that I can't overcome this, right now. So there will be no conduction. So this is the source side, this is the drain side. And this is represented by this dotted line here, okay? Now let's take VGS is equal to V. So I don't know why. 1 second. Okay, so now let's take the condition VGS equals to, let's say just at VT when the channel is formed, and VDS is equal to 0. So then your potential kind of looks like this. I'm just showing you that it's flat basically, right? Because now you have a channel, there is no potential barrier, but you don't have any potential difference as well. If you don't have a potential difference, then there won't be any electric field, right? You need some dV over dy to create an electric field, then you can conduct current. So there is charge now. Now you have the potential to conduct current, but you don't have any electric field to conduct it, right? So now you apply so now let's take the condition VGS equals to VT, but now VDS is some positive amount, right? Greater than 0 volt. Then on the source side, it remains the same, but on the drain side, it is lower, right? By the amount Q times VDS. This is the energy of the electron. So now this energy of the electron here is higher than energy of electron. Now they can flow. Or in other words, this slope is E is equal to d phi over dy, and then V, the electron, is equal to mu times E, and then they can start flowing now. Okay, so this is how the current, but the thing is that because this field also has an effect, because as you're lowering this side, it is actually, you know, extending till here, but in long channel you don't see that because it doesn't reach that effect all the way here. In short channel you reach that effect, and this has an effect on the VT, because VT is basically telling you how fast you're lowering this barrier for a given gate voltage. So the drain is affecting that, and because of that, your VT is affecting.
Okay.
Did that make sense, Srishti, or who?
Yes,
Who's,
yes.
okay. Okay, good. So very good explanation of this is by book by Cividis. It's called, what's the book name? It's called the MOS transistor by Cividis, and the newer edition has another author too, but it's mostly. So for device physics, if you want to go really deep into device physics, this is one of the best books to refer to. So you can find a very detailed description on this one. Okay. All right. Any other questions? All right. So now I want to. This is nothing to do with short channel. Subthreshold conduction is actually there in the long channel as well. If you guys remember when we did the VGS versus ID curve, right? Obviously so if we did the ID versus VGS, our equation predicted this, right? Just 0 till VT, and then suddenly, you know, you have the square law relationship. But in our simulation, we saw that actually the current is increasing before that too. And that's what's called the weak inversion region of operation, which has conduction. But here, so when you get to VGS equals to VT, the channel is obviously formed, but before that it's not magically off, right? That's just a arbitrary point we took to make our life easier. So before VT also there is a channel, but it is weaker, and then few tens of KTs like 20, 26 millivolts or 100 millivolt before VT, there is no channel, but you can still have conduction with diffusion, just like in BJT. So I've shown a BJT here, right? So basically this is your N, P, N, right? Just like in a BJT. So you have an N plus region, N and P. In this case, we have N plus P, N plus, but it still looks like a BJT. So if you remember in a BJT how it operates, right? In a BJT, you forward bias this diode, right? So you have an NP. So you forward bias this diode. Sorry, I'm showing the reverse here. This is NPN. So this is this direction here, right? So you forward bias this direct. So when you forward bias, the majority carrier for P is actually holes here, right? So you have a huge amount of holes injected into the base. But the thing is that because you have a collector to base voltage, right? You have this collector to base voltage. There's a huge electric field from base to collector, actually in the other direction, sorry. So in this direction, right? And the holes are a minority carrier here. Because you have electric field from here to here, these carriers which are generated here, they're actually captured in the collector before they go into the emitter, right? So that's how the current actually looks like, as if it's flowing from collector to emitter, not from base to collector. That's the mechanism of, excuse me, for a BJT. The subthreshold region kind of looks like it. In fact, it looks very much like it. The only difference is now you don't have a connection to base directly. You don't have this connection here, but instead you have it through this capacitor, and this capacitor is Cox. Okay, so which is here. So essentially your base kind of looks like this. So you have an N plus, then you have a P region, then you have an N plus, and you have a capacitor Cox, you have a capacitor C depletion, and that's connected to your base here, which is your bulk. And then this looks like your emitter, let's say, or collector, depending on your voltage. So in this case, it'll be emitter, and this is your collector. So your base voltage is kind of, sorry, kind of a voltage division of Cox C depletion, right? So VGS. And then it's the same mechanism. So you have a potential here, which is looking like the base potential. And because you have some minority carrier injected from here, which gets swept away to the drain side, and you get a current. Now the current is very small, but so this is, so the subthreshold current, honestly, I've, you know, you see every book, it's different, but actually the Hodges book has very close to what you have in the BC model. If you go into the BC model, it's pretty much close to this model. It's much more complicated, but at least in principle, this is. So you can see this. So if you remember BJT's equation, right? What's the BJT equation? The collector current is some IS times e to the power VBE over the thermal voltage, right? It is 1 plus, but approximately equals to 1 ES times. If you look at the threshold, subthreshold current, conduction current, it is Q times VGS minus VT sum of, this is a fitting term, but it almost looks like, you know, this is your VB over KT, but there is a eta term, and this eta is, you know, around 1.2 to 2 term. And that is actually, in a lot of books, you'll find is actually the voltage division of this capacitor here, Cox in series with C depletion. So essentially you'll see that, you know, C depletion times Cox over C depletion. This ratio is what is eta in a lot of books, but it's actually a fitting parameter. And IS obviously depends on your W over L times mu and Cox and so on. And then you have this VDS term, which basically tells you if your VDS is really small, then this term is, you know, the subthreshold current is low. And once it goes higher than that, then it almost becomes 1 basically. Okay, so that's your subthreshold current. So you can see it has a huge exponential term compared to a square term, right? Your saturation current, it was VGS minus VT square. Here it is VGS minus e to the power. So in analog, we actually use this region of operation a lot because we are always looking for high gain for a lower given amount of current. So you can see that here you get actually higher gain in the sense the delta I over delta VGS is what you're looking for. Okay, you're not looking for absolute I, but delta I over delta VGS, right? This is really high for subthreshold current, and it could be as high as 6 to 8x higher than saturation current for a given amount of current. So that's why people in low power, and if your speed is not high, because the problem here is the current is really tiny. So if you want to drive a large amount of capacitor, this is not the best place to bias your transistor in. But if you have a really small capacitor and you're swinging the voltage very small, but you want rapid swings, then this is a good area. Like for example, in amplifiers in analog where it is low power, but you want high bandwidth, then you use in this region to get a delta I over delta VGS, very high delta I over delta VGS for a smaller amount of current. Okay. So that you know. So today in the lab when I do, I'll show you again, through this lab. So, when you did this curve, right? The VGS over ID curve, you just saw that, right? VGS over ID curve, you saw this. So you couldn't, so when I'm saying that this slope is much higher than this, you might say, oh, this slope looks way smaller than this. Oh, that's because, this current was so much higher than this. It's just hidden. You can't see it. So if you instead plot it in log scale, now this is plotted in log scale. Now you see this for VGS less than VT, you can see the current is really small, right? The current are tiny, but you can see the slope is much larger than the slope in the linear or in the saturation region. And like I said, in analog especially, you use this to our advantage a lot, especially low power circuits. You use this to a large advantage. Any questions on the subthreshold one before I go to the next one?
No, sir.
Yep, go ahead.
No, sir,
Yeah,
no
what's
questions.
okay? Good. So so far we've been saying that VGS less than VT, ID is equal to 0. That is not totally true. You know now that there is a small amount of current flowing, but it's small. So for high power devices and so on, we can take this approximation. It's fine. But if you're operating at a lower voltage in subthreshold region, then you have to use accurate model. And the models now, see when I started designing, back in the late 90s, nobody ever used subthreshold region to fabricate that chip because the models were so bad. They were not models. So when the chip came back, um, it just won't, it'll be completely off. Like your chip essentially would be dead because the models were very bad. So, but now the models are very accurate. So you can actually drive it into subthreshold, and whatever your simulation is showing you, when you get your chip back, it'll be like 99.9%, accurate. If it is low frequency, if it's high frequency, it's a different deal. But unfortunately, a lot of the designers, still old designers like me, they still hold. Not in the sense that I use subthreshold, but a lot of designers who have been designing for a while, they still kind of hold that fear that no, I'm not going to design in the subthreshold because the models are bad. So they're not bad. Now the models are really good. So you can design it in subthreshold now if you're using BSIM4, and when your chip comes back, it'll be very accurate. Obviously, the foundry has to do the job of making sure that they are giving you the right fitting parameters. If they're doing a poor job, obviously it'll be off. But the model itself is capable of modeling subthreshold, which was not the case in pre-BSIM3, BSIM2 region. Okay. All right. So I'm kind of randomly covering different topics now, which are sort of very useful while designing. Also, kind of pet questions for people when they're for interview questions as well. So like I said, um, just you have to just work. I mean, it's difficult to cover all these topics in detail in one session. So I'm just covering them and giving you sort of the idea behind it, but you really have to dig deeper into it to know the details behind this. So latch up is probably one of the crucial. So when you start doing layout, you have to worry about latch up all the time, and and it's to do with a parasitic NPN PNP configuration, which results when you have NMOS and PMOS sitting next to each other. And this is what's called, when I was showing you different, um, I showed you two different processes when I was showing you the fabrication process. One was locus, which is this. The other was STI or SOI. So in SOI and STI, this effect is obviously smaller. It's still there. But in locus, it's larger because the substrate is basically shared by the P and the N type. Okay. So here, if you see, this is an NMOS, obviously. So this is, let's say, your source, drain, source, drain of your PMOS here. So this is your NMOS here, NMOS gate, and your PMOS here. Okay. Now, what's drawn here is to show you that there is an NPN structure here, which is kind of parasitic to this NMOS, PMOS sitting right beside each other, right? So because you have this N and you have this P, right? So you have the N plus, you have the P substrate, then you have the N plus and the N well, and then the P plus contact for the N well. Sorry, this is the N well contact here, N plus contact. This is your P plus contact for your N well. And this is N plus contact, and this is your NPN. So essentially what you get is you get these two BJTs. So you get an NPN and PNP, and this NPN is the N is the source side, P is your substrate, and this N is basically this N well here. This N well is the N for this N, right? For this PNP, this is the PNP diode. The P is obviously the P plus of this drain. The base N is this N well here, and the collector P is this P substrate here, P substrate over here. And if you draw this, you'll see that there is a resistance obviously between everyone, but in between all these nodes. So there is a resistance here, there's a resistance here, and so on. But if you simplify this, you'll see that you have this NPN with a resistor connecting from the base to this, because there is a finite amount of resistance because of this P substrate here. Similarly, there is a finite amount of resistance from the connection made to the N well to this sort of this parasitic B because of a finite resistance, because you have a sheet row, right? You have a R sheet for this N well, you have a R sheet for this P substrate. Because of that, you get these two resistors. Okay, so now if I draw the simplified diagram, like I said, there are resistors all over the place, but these two are the crucial ones. Okay, so you have this structure now. You have this back-to-back NPN PNP structure. And what does this do? So this is a parasitic structure, right? So essentially this should be sitting at 0 volts, the VB here, and this BB is also should be sitting at 0 volt. There should not be any current flowing through this because it's a parasitic structure. There should not be any structure. And this voltage is supposed to be the same voltage as this, because this N and P are sitting at the same voltage, right? This is your N well, this is your VDD, so they should be sitting at the same voltage. There should not be any current flowing to them. But now let's say you have a coupling capacitor. Now in IC design, like I say, there's a coupling capacitor from every node to every other node, right? So obviously you have a coupling capacitor here. So now let's say this was output of some inverter, some high power inverter, right? And this is some clock going in back and forth. So you have a huge signal going back and forth. So you have a huge dV over dt. And you have a huge dV over dt. What's the current through this cap? I is equal to C dV over dt, right? So you'll have some current flow through this, and that current is flowing through this resistor, right? And it is going to drop some voltage. So let's say it drops, I don't know, 0.1 volts, right? That 0.1 volt, this BJT is going to start conducting now. It's not 0 now, so it's going to start conducting now. So there is going to be a current flowing through this. So this is going to drop a voltage Just give me a second, 1 second. Okay, so there's small current which is going to flow through it, which is going to drop here, right? Some I times Rn is going to drop. So there is going to be some voltage drop across this. If there's some voltage drop across this, then this collector voltage is positive now. I mean, negative, we see negative right now. This PNP is going to start conducting. That means there will be more current. That means there will be more voltage here. That means there will be more current here. That means there will be more voltage here. That means there will be more current here. And basically what it is a positive feedback now. And essentially what this is like a SCR latch, right? So it'll SCR latches are formed that way. And then this will go to 0.7 volts, and you can see then it'll clamp the VDD. I mean, it'll get it down to, whatever is the lowest voltage. So let's say the VC was 0.2, this VB was 0.7, then the VDD is going to go from 5 volts to 0.9 volt, but there will be a huge amount of current flowing from VDD to this thing, and it'll basically just fail the circuit. Okay, so most of the circuit actually fail because of that. So how to avoid it? So think about it. So now tell me, just from this circuit point of view, if I gave you this circuit and I said I don't want this, what can you do in the circuit first to avoid it? Who can answer that? Just looking at this PNP circuit, to avoid this latch up, what can you do to avoid it? Anyone? How about you, Satya? Can you at least speculate how can you avoid this latch up? How about Shruti? Someone just like, what I mean is, in this circuit you can come and tell me, oh, just reduce the beta of Q2, or change the resistance, or remove the resistance, or remove the transistor, something like that. Something like that in the circuit. What can you do? Alok? Any ideas? Srishti, any ideas?
Yes, sir, I'm just thinking.
Okay, so what is creating this whole positive feedback loop? Obviously having the two transistors, right? So you can say, oh, just remove the two transistors, but that's um, part of the PNP structure. If I remove the transistor, I have to remove the MOSes. That's no good, right? So you can say, oh, reduce the beta, right? Just make the current less than 1. If your beta is less than 1, then you won't have this increasing current. The current will just keep decreasing and they'll never latch up. That's one way. But again, that I don't have in control, because when the MOSes are made, you need a certain channel doping for VT, you need certain doping for PN and all that, right? So those are really decided by the MOS transistors, right? Now, what
Sir,
about these
maybe
two?
by increasing the doping concentration, we
Good,
can
yeah.
control.
So you can change the doping concentration, but like I said, the doping concentration really is decided by the MOS transistors. So because if you change the doping concentration, your VT will change or your mobility will change, and you don't want that to happen, because you don't want to degrade your devices as well. I mean, it's always a balancing game. So you drive that to the maximum as you can, and even after that, you'll still be left with certain betas which are greater than 1. Um, But the other thing you can do is you can reduce this resistance, right? This resistance, because let's assume that this resistance was 0, then you don't have any problem, right? If this resistance was 0, this resistance was 0, then this VB is always equal to 0, this VB is always equal to 0, then you don't have any problems, right? So if I go back to the layout here, what are those two resistances, right? Those resistances are so if you see, uh, we the P substrate, we have been always showing that we make a contact here, but this is a planar process. Every contact has to be made from the top. You cannot make contacts here, right? That's the bottom. I mean, in some process you have baguettes, but all your transistor connection has to come from top. So when you're making from top, this substrate, so let's say this contact was made here, somewhere here. Now this resistance is even more, right? Same thing. This NVL was, let's say, all the way here, and you had few more devices here, and you made your N plus contact here. Now your contact resistance is even higher, which means this resistance is even higher. That means the potential of dropping the voltage for a smaller current is higher, which means now it takes a small amount of dV over dt to latch up. Okay, so this resistance is really the key. This resistance, all this resistance is not an issue. Actually, they will help you prevent a latch up, all this resistance. But the resistance from this sort of this fictitious base to your source connection is the problem. So if I show you layout wise, so let's say this was your diffusion area for your NMOS, right? And so this is your diffusion area for your PMOS, and then your gate area, your gates are this, right? So this is your inverter. And then you make the connections, drain to drain connections, right? You're drawing layout yesterday. So you did a via here, this is metal 1. And then you did substrate connections. You remember you did substrate connections, which is basically adding a P plus diffusion here. So you have added a P plus diffusion here, and then you added a N plus diffusion here, right? You added N plus diffusion here. This is N plus, that's P plus. And then you took metal, and this is your drain connection. So and this whole metal connection to your substrate. So this is VDD, right? You would connect to VDD, and this metal, you would connect it here, you would connect it here, and this would be, sorry, I think I have it upside down. This is your ground because this is your NMOS. This is your VDD, right? So this is how you did your layout yesterday. And obviously you connected your poly. This is your input, VIN, this is your output, and so on. And this is where you brought in your supply. This is your ground. Now, this distance is what is creating this RP here. RP here. And this is your RN here. So you remember how you calculated. So this is a block, solid block of material, right? From here to here. Right? So what's your calculation of the resistor? Remember RP? What is it? Sheet row of the bulk material, R sheet of whatever RSP times L over W, right?
Yes, sir.
So W is basically this here, L is this. So if you want to make RP small, what do you want to make L? L also should be small, right? This length. This should be small. So in other words, when you're laying out, you want to make sure that you have a substrate contact either to your P sub or to your N-well. So this is your N-well contact, right? So this, you would have drawn N-well and drawn N-well contact. They're as close to source drains of your active devices as possible to minimize these two resistances. Okay. If you have this like far away, once you get your chip back, probably it'll latch up and just burn the whole chip. Okay, so for example, in analog, when we do design, like we have a, a rule of thumb that when we stand on top, like if this was a street and and you stood on top of this diffusion here, like you were a guy who stood up this, and you looked around. So you want to see a connection to a substrate within 5 micrometer at least. If you absolutely cannot do it, we keep it 10, but 5 is wherever we can do 5, we do it. If it is going to take too much area and all that, we resort to 10. This is just from experience. People have, got burned by getting latched up, and because once you get a latch up, sometimes very, very difficult to debug. And people use infrared cameras and all that to see where the heat is coming. A lot of times you still don't know, because these are all parasitic devices, and you would be, scratching your hair, but somewhere you would have had this small connection, and that would be latching it up. So that's why you have to be very, very disciplined in making these substrate connections spread all throughout. Okay. So everyone clear about the latch up? So it's basically a parasitic device, NPN, PNP, back-to-back connected. The key to the latch up is, if somebody asks you latch up how to minimize it, basically the key is you have to make sure that the substrate and the well contact for all your active devices, your NMOS or PMOSs, wherever you have laid them, should be as close as possible. How close? Nobody knows. Like I said, we use a, nowadays, obviously people do a lot of, because it's dependent on so many things. It depends on how thick is your W is your, like I said, it's also dependent on your W, right? If you have a really wide this thing, then you could live with this kind of a um, longer L, but you don't know that, because this is all decided in the layout. But there are certain rules which people have found out throughout the years, and they are included in DRC. So when you do a DRC, like you did a DRC yesterday, um, and you did LVS, in your DRC, typically this rule you'll never find. So this is something as a designer, you just have to, you have to make sure that it is. But not a lot of the newer technologies, they're trying to put some of these latch up rules into the DRC, so that, because it's getting so complex, that, because it's cost millions and millions of dollars for people to spin each time they make a mistake, it's a huge cost to companies. Okay. Any other questions? Okay, so I'm just process variation. I just gave a title slide, and I'm just going to quickly talk about it. In IC fabrication, the parameters, like all the parameters you have been calculating, right? You calculated mu naught, VT, and so on. Like, let's say mu naught was given to you as 570 centimeters square per volt second, and VT you calculate to be 0.5 volts, and so on. These they vary over process. And what do you mean by process? If you remember, on when in our first class, I gave you the whole um, design flow. So you do a layout and all that, and you send it to the fabrication house, right? So you do all your layout and send it to the fabrication house. They take this circular 8-inch wafer, and they process your chip, and then they cut and slice and dice it, and then you get this chips, which you package them, and you kind of bond them out, and you get this nice packages, which you put it on your breadboard and start testing, right? Now the thing is that each time it comes out of the fab. So let's say, I made a radio chip or a cell phone chip, right? And I got a order for 10 million chips, and so I sent for whatever, 100 wafers or something like that, or 300 wafers, right? I sent an order to the fab house. XFab, let's say, is one house we use, XFab. So they're going to process maybe 300, all of them together, or maybe in 3 different batches. But let's say they used one batch, right? They do it. Or let's say they use, okay, let's consider one batch. In one batch, they did all 300 wafers, and I got this 10 million chips. So when I get 10 million chips, I measure them. All of them, let's say mu naught came out to be 570. There is a local variation, and and that's what we call local mismatch. So they'll vary. So there'll be, if I draw the graph of mu versus number of chips, they will be all around 570, but they'll actually have a Gaussian variation. Okay, same thing. This is what's called local variation. Okay, so they'll all be 750. Same thing when I measure the VT, they'll be all around 750, but they'll have a local variation. Will depend on the size and all that. It might be few millivolts, like 2 millivolt or even 10 millivolt, depending on the size and so on. Okay, but all the 10 million chips will be around this mean. Okay, the VT, mu n, and other parameters will be around that. So this was in, let's say, 2019. In 2020, I get another 10 million orders. I get 20 million orders. So I sent XFAB. I want 600 wafers, processed. The layouts are with them, so they use the same layout. And this layout, let's say, had two batches in the sense they couldn't. Their capacity is such that they can't do 600 at one time. So they did 300 at one time, 300 in another time. I get 300, and suddenly I find out that the mu is actually all slower. So they're all like 400 centimeters square per volt second, right? One batch. So they still have some local variation, but they're not anywhere close to the 570 I got before. So they're over here. So the first batch in 2019, I was here. Now I'm here, 400, right? I see the second batch, and suddenly the second batch is all even higher, like let's say 700 centimeters per volt square second. Same thing, when I measure the VT turns out to be lower now. Maybe they are like 0.4 volts. Okay, this has some local variation, but they're not anywhere close to the 0.5 I had calculated before. So this batch VT is all small. And then I take this 300 batch and I start measuring all the 10 million chips, and all of them now is higher actually. They're like 0.6 volts, let's say. Okay, they have some local variation, but they're around that 0.6 volts. And this is what's called the process variation. And you remember when you're doing your SPICE simulation, Santanu made you do the different process corners. So you have that .lib, right? / project 20, blah, 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 and SCN, blah, blah, .lib. And then you follow with this thing called nominal, right? NOM. This is what's nominal corner, or what's called a typical corner, which means that typically you're going to get this. Means typically your mu is going to be 570, your VT is going to be 0.5 volts, close to that. But they will give you these extreme corners. So like, for example, you've already done this lab where you do I think it's called slow, right? Slow. That means it's a slow NMOS, it's a slow PMOS. Okay, you do that, then suddenly your mu is this and your VT is this, right? And then if you choose your .lib, let's say fast, this is called slow. That means slow NMOS, slow PMOS. And if you do fast, this is a fast, both of them are fast. Then you would have your mu as 700 and VT as 0.4, maybe something like this. Okay, so in our lab today, because we also get introduced to Python to automatically extract these parameters, so we can do it fast. So today we are going to do this process and use a Python script to extract these parameters, and you can see how they're varying over process and temperature. So when you start going into the VLSI industry, you're going to hear this PVT term a lot. PVT. Have you done simulations over PVT? PVT. Have you done PVT some? So the PVT is the acronym for process. Okay, and this is for voltage, and this is for temperature. So you have voltage variation because your battery is going to vary. It's not going to be exactly 3.3 volt. It's going to be 2.28. So you want to make sure that for your entire battery voltage variation, your circuit is performing well. Process is the part I just explained. You want to make sure for all corners, these are called process corners. Okay. So when people said, okay, is it working in the slow corner? That's what they mean. So all corners. So for process corners, you want to make sure that you're meeting the specifications of what your chip is supposed to mean. And then temperature, right? Because all IC, like your phone or anything like that, like consumer items, for example, they have to work between -40 to 85 degrees centigrade. But that is ambient temperature. but your junction temperature could be as high as 125 degrees centigrade. Industrial ambient actually has to work from -40 to 125. Automotive and industrial, they have to work with very high ambient temperature as well. Okay, so I'll talk about a little bit about the temperature variation afterward. So everyone clear about the temperature variation now, or any questions? Okay, so maybe when we do the lab, I mean, you've already done the process variation, hopefully. So it's basically batch to batch. Every time you send, every time they're fabricating in a batch, your parameters, your mobilities and your threshold voltages, they can vary. But they'll give you bounds. It's not like they can vary all over the place, because then it's unpredictable. They'll give you predictable bounds. So, and these bounds are the corners, basically. They're called the corners. And the corner name comes because it's usually a matrix of process and temperature, and you're essentially, or the binning. So you basically want to make sure all the corners of the process temperature and voltages, your spec meets within these corners, basically. Okay, like a temperature. So in semiconductor, just give me a second. So semiconductors are very sensitive to temperature, right? Everything varies with temperature, and because of which all your parameters inside your MOS also varies with temperature, because they're all related. So, so one or two of the things which are dominant, temperature dominates in MOS equation. I'm just going to quickly talk about it. So first one is mobility. So mobility, the phenomena of mobility comes from the fact that as the electrons are traveling at a high speed because of electric field, they start banging against the lattices of the silicon structures, right? And because of that, you get what's called phonon vibrations. It's basically a quantum effect. It's essentially, it's like generating heat and slowing you down, right? That's what is slowing you down. And then eventually you hit a sort of a terminal velocity, and that terminal velocity is what is the constant, because like I said, your V is proportional to electric field, doesn't keep accelerating all the time. So this constant is your mu, basically. But obviously, as your temperature increases, this lattice vibration increases with it, because they get more energy and they're trying to break away from their bonds. And so this lattice vibration increases, and this lattice vibration in turn slows you down even further. So in other words, in the constant we measure, we see that it drops with temperature, and that's typically given by this equation over here, where TR is basically your reference temperature, and typically that's about 300 degree K. So it's whatever is the mu at 300 degree K, let's say, then T over T, TR minus this constant, and this constant is usually 1.222 value, depending on the type of material and so on, how you fabricate and so on. Okay, so that's this. So because it's the inverse, so obviously this is mu TR over T by TR. So it's inversely related to the temperature, which makes sense, like from what I explained right now, right? So the mobility is inversely proportional to the temperature. Now the threshold voltage, right? So if you remember the expression for threshold voltage, VT is what, 5GC minus QBC ox minus 2 phi F, and then you get QDI Cox and so on. So this one also has a temperature dependency, and primarily due to this work function and the phi difference. Now, because there is a negative term here, and 5GC has 5G minus 5S, they tend to reduce your VT. So this actually has opposite effect, where VT actually, you can write maybe VT, somewhat similar to this, where you can write, let me write it somewhere here maybe. So you can write VT as a function of temperature, which is equal to VT at some reference temperature, let's say 300 K, like we did here, and then some constant times T minus TRF, right, reference temperature. And this is your temperature coefficient, which is like here I've shown -1 or sometimes even -0.5 to -2 millivolt per degree centigrade. In other words, every degree centigrade, your VT is going to change by 1 to 2 millivolts. Okay, and it'll reduce. So for example, let's say at 300 degree K, your VT was 500 millivolts, right? 500 millivolts. Then at 301, or let's say 310 degree centigrade, degree K, it's going to be, if it was -2 millivolt per degree centigrade, then it's 2 times 20, 10 is 20, so it's going to be 480 millivolts. So at a higher temperature, it is lower. So 10 degrees higher, it is 20 millivolts lower VT. Okay, so that's the threshold voltage. And then the subthreshold current, you know, that IS, I had shown you that IDS at the subthreshold current is equal to IS times e to the power VGS minus VT, some Viosa times N times KT, right? So this actually increases because you're mostly because your minority carriers are increasing in the temperature, right? So you can see the Ni is increasing as the temperature goes up. So that actually increases the IS term in your um, subthreshold current, right? So so what does this have effect? So how does your IDS vary as a function of temperature? Okay, so I'll just show you, and we'll do this experiment also in the SPICE, and it'll be more clear. Then you know how you did the root IDS function, right? If you do the root IDS now, you'll see that you know it's proportional to mu, which is a function of temperature, and then you had half you know W over L Cox over some alpha, and then VGS minus VT, right? It was proportional to this, which is VT is also proportional to temperature. Right? So you can see from this equation that you have a mobility which is decreasing with temperature. You have a VT which is also decreasing with temperature, but this is a subtraction, which means that this excess voltage actually increases, right? So one term is increasing, one term is decreasing. So when you plot versus temperature, and we'll see this with our similar when we do the lab today, you know, that root ID plot you did. So you kind of got this linear, let's say, right? Then as the temperature increases, you'll see that this slope obviously decreases, but it actually will start increasing after a certain point. And then, you know, I'm kind of exaggerating it. So this is decreasing with temperature, and this is increasing with temperature. Okay, so and this is typically around VT. So above VT, you'll see when it is well saturated, the mu is dominated. Okay, the VT decrease is not that prominent. Your mobility is actually dominating most of your current. Below the subthreshold, this is what, because your mobility is not that big of a function of temperature at, you know, at that, I mean, the mobility is, but because your VGS minus VT has exponential term here. So that's what is actually, it's not because of the exponential term. It's because the VT term is more dominant here at this temperature than it is for the mu. And so you see it's increasing. Okay. And we'll do a log of this, but this doesn't mean that I told you, right? The slope is much higher than the slope is still decreasing. It's just that the absolute current is increasing in subthreshold. So it's not, doesn't mean that higher temperature, I'll get higher gain from an amplifier if I have in subthreshold. The gain is still going to decrease, but the subthreshold current, which is kind of a leakage current, that is going to increase. So you actually find, you'll find one point here you'll find one point which is almost independent of temperature. So this idea is here is, so if you can bias it at exactly at this point, it'll be almost independent of temperature, right? So, independent of temperature. And in analog, we actually look for temperature independent current because that's how we bias our circuit and all that. But we actually don't use this method because there are easier, less, because it might seem easy from here, like, oh, just find that voltage, set it. But doing it in a circuit is very complex. It's not that easy. So there are other easier methods to, get constant current. So we use that instead of this. Okay, so these are the temperature effects. So your mobility goes down, kind of makes sense because you're banging against this hot lattices and it's just forcing you down. And so that's why it goes down. And your VT also goes down because you have this 5GS term, 5S term, which are negative terms, which are increasing. And that's the overall VT term is decreasing. And it could be as high as 2 millivolt per degree centigrade, the temperature coefficient. And then the subthreshold current increases mostly because the minority carrier increasing. That's the mechanism of subthreshold current. So that increases. Okay. So just, again, these are the equations. You don't have to worry about those equations, but you should know the behavior. Like somebody asks you, is the current going to increase? If I'm in saturation, is the current going to increase or decrease when the temperature goes higher? You should at least know that, oh, it's going to decrease. Same thing, if somebody tells you that, oh, I'm deep subthreshold, is the current going to increase with the temperature or decrease? You should know at least that it is going to increase. And VT also, how is VT changing? And, when you are a designer, especially analog designer, you don't need to know the exact terms, because when you're debugging some circuit, let's say I get a chip back and I find out that I have a high temperature problem, right? Just knowing these behaviors will actually get me on the right track. I'll say, oh, if it is high temperature, it's got to be low VT, it's low mobility, it's probably a mobility issue. I'm running some headroom issue and must be an issue with this and MOS or whatever it is, right? So once you know these behaviors, it'll lead you to the right directions to do debugging and design properly. Okay, any questions? Like I said, we're just introducing a lot of sort of terminologies and concepts today, but that's okay. Like I said, once your base and foundation is solid, these things you can pick it up later by reading it, but at least the principles you should be able to follow. Okay. Here I'm just showing you those effects, basically showing you that subthreshold current. You can see over here as temperature is increasing, it's increasing a lot. And then the saturation current for NMOS and PMOS, it's decreasing as the temperature is decreasing. I would do a lab today and we'll see these effects as well. Okay, let me show you quickly. So so we went from like level 1 equations and we showed you some fitting parameters. But if you look at the model, they're even a lot more complex than this, just to get the exact results. So let me bring in. Okay, everyone can see the browser window here.
Yes.
Okay. So this is the BSIM 4.80, which is probably a very, it's 2013, but that's the most recently, one of the most recent ones used. Okay. And, obviously you can see there is a model for everything, the effective oxide thickness, channel length, a dielectric model, polysilicon gate depletion, which we haven't taken into account at all. So there is obviously polysilicon is a silicon material, so it's going to have some depletion. Threshold voltage model. So let's take a look at threshold voltage. So you can see this obviously you're used to. This is our first order equation where we take VT0 gamma times this, where gamma is this first order equation. And then for non-vertical doping, you see we added that K1 and K2 terms. So they add this K1 term, which depends on the vertical doping concentration. And there are more fitting terms here. Let me show you. Maybe see this K1, K2, which I showed you for BCN3 is pretty much the same here as well. Then you have non-uniform lateral doping, which is called the halo implant they do. So as the shorter channels get shorter, it's very difficult to keep the doping constant. So they do this halo doping. So the halo doping effect is taken into picture. And you can see there are different models for different widths, lengths. So they bin it heavily. Like what is the length? What is the um, um, width, and some on voltages as well. So depending on each width, there are a lot of modeling parameters, and you can see the short channel DIBL effects is taken into account, which we discussed about, and the classic short channel, the reverse short channel. I don't know if there is a complete equation somewhere. Let me see. Then you have the narrow width effect, which we haven't talked about at all. We just been talking about length, but the narrow width also has an effect. So yeah, you can see here, this is one of the equations. So you see the complete equation is this gigantic. So you can see there is a VT0 here, but after that, you can see that it's just a gigantic number of empirical fitting, which is done after the chip comes back, they measure it and all that to make sure it matches. So when you're simulating, you can see how complex these equations are just for one, VT equations, how complex the equations are. Okay. Same thing you can see subthreshold channel charge and subthreshold models for each one. I mean, we take channel charge as QI equal to Cox VGS minus VT, but obviously there's a lot of parameters, the effective length, the depth, and there are fitting parameters for everything. And you can see here, it's Cox effect, VGS effective, but there is a lot of fitting parameter which goes into. So we take the simplest channel charge equation which we derive, but there is also a lot of channel charge equations which are a lot of fitting which goes into this. And for the subthreshold, yeah, you can see here we kind of use this equation again, a lot of fitting parameters into each one of them. The n is this big parameter here. Each of these has fitting parameters which are calculated on top here, and so on. Direct tunneling, which we haven't talked about because we have been assuming that this is a thick oxide, there is no gate current, but there are quantum effects once you're talking about channel thickness oxides which are as thin as 7 angstrom or 8 angstrom thick, right? So because of that point, you get what's called quantum tunneling, in the sense that the probability of finding the electron from this side to this side is no more zero like before, or close to zero. So it's a large positive quantity. So once you go down, even 65, 28 nanometer down, and obviously once you get to the 4 and 5 nanometer, you actually get gate currents which are substantial in nature. Gate to substrate currents, partitioning of IGC. This is drain current. So, and drain current, obviously there's a lot of unified mobility model. So you saw we use this mobility model here. Let me enlarge it a little bit over here. We use this mobility model here, but that's like the first order fitting. You can see here, the fitting parameters are huge for the mobility itself. And they're different for different modulation, different model binning models, right? So like mobility model 0, mobility model 1. I don't know what these models are. You have to read the manual for, but depending on how it is manufactured. Depending on a certain process parameter, you have to choose either this or that, and that's decided by the fab. So fab already does this selection. So for example, if I'm getting a model from TSMC, they would have figured out, okay, our model needs this condition, mod equals to 1, because it needs all this effect of width and length and so on. So they would actually set this in their model and send us. So when you get the PDK, these are already set. You can see how just for the mobility, how complex and how many models there are. There are like 10 different models just for one of them. Anyways, just to kind of give you an idea, how much goes into these modeling. So what we have been doing so far is just a first order modeling. Even the correction we have done so far, it's a first order, because each one of these is a huge amount of equation. And velocity saturation you can see over here. So this is what we use this today to calculate the velocity saturation. Again, the model is much more complex than what we use today, so there's more to it. And you can see, and you can go on, because this is like 200 pages of just modeling equations. So anytime you're in a model and you say, oh, I don't know what this is, you go into a model and you see all these parameters, I don't know what it is, you just open the manual and it'll tell you exactly what this model parameter and how they are modeled. Okay, so I just wanted to give you an idea on how these are modeled. Any questions? Okay, if you guys don't have any questions, I think that's all I have. So what we're going to do in the afternoon's class is we're going to see some of the temperature effects. We're going to vary the temperature and plot some of these plots and see if they match what we have claimed so far, like the mobility and the VTs and so on. And then I'm going to introduce you to the the Python API, which I said we have as part of the CPP Sim software, which Mike Perrault wrote. He also wrote a very good API for Python. So we are going to use Python to extract some of these parameters. So we'll do ngSpice run and put the output in output file and read this output file into the Python script. And then once we have loaded it, then we have the entire Python at our disposal to do anything we want. And so what we're going to do is we're going to calculate some of these parameters which you have done in hand. And you'll obviously see that, once you automate it, then we can just quickly check a lot of things quickly. Obviously, I'm not going to expect you guys to know all Python. So that's why I've already written majority of the code. So we are going to just do a JIT pull, get those codes, and then I'll go through each of the lines code. It's very simple, and then I'll ask you to maybe add. So like for example, I've already done for VT extraction, and then I'll ask you to do just for the mobility. Okay, we'll do that, and we'll look at the process corners and see how they're varying with the VT and all that. So today will, in the lab, you'll get an idea on how to, looking at temperature variation and seeing how they're varying with temperature, and also learn to use the Python toolbox. I mean, it's a really powerful toolbox. Once you learn that, then, not only, I mean, you have the exposure, because, you've probably seen that you're a little bit limited with the plotting tool. So once you read it in Python, you have the entire matplotlib, which is the popular Python package for plotting. You have the entire toolbox at your disposal to do that. Plus, you can do all the post-processing calculations and all that without, and then, generate files based on that, like the .lib files. You can generate .lib files from this Python API, basically. Okay. Any questions before we sign off.
No, sir.
Yes.